So hello, welcome to the coursework for signal processing for millimeter wave communication for 5G and beyond. So my screen is visible, I think. Is it so?
Yes, sir, visible. Sir.
Okay. So the first question is the baseband equalizer in millimeter wave MIMO system data detection is not required for. So let me solve the question first here. So the first question is baseband equalizer. So why do we do this? To mitigate the problem of channel. The effect, I would say. So only thing we do the equalizer design is to avoid the search process. That is required for ML estimation algorithm. This is the basic need for equalizer. Like we want a some
Sir,
sort
avoid the
of
search of.
yeah.
What you have written, sir?
Avoid the search. Like you have some signal y, and you have something like hx. So for which x, this y minus hx, this term will be minimized over all the x values, right? So if you have to search over all the x values, here you have to do the search. So this, if x is very is a vast space, like m to the power nt type of thing that I have discussed in the earlier session. So if the number of search space in the constellation space is very high, I mean there are m number of antennas or nt number of antennas or m number of constellation points, like MPSK the system is. This constellation search space become m to the power nt at this instance. So the main thing we do the equalizer to avoid the search here. So that is the reason we design the equalizer. So in the question it is mentioned the baseband equalizer in millimeter wave MIMO system data detection is not required for. So if we do the ML based detection algorithm here, so at that case we don't need the baseband equalizer part. Like all the other things are low cost solution, and probably they will not match the exact QoS parameters like error probability, BR, all these things will not be matched if we use such sort of equalizer based design. ML will give me the best thing, best detection thing, but for low cost thing we can use this sort of equalizer designs like LMMEC based and least square based and MRC based equalizer, and all these things we can use. So we don't need to do the equalizer design if we actually doing the search y minus hx and over which x, for which x this cost function will be minimized. This is the cost function we have to detect, y minus hx. So if we do the search, then we do not need to do the equalizer design. If we do not do the search, then we can design some equalizer. Like for LMMC, what we do, we just multiply this y vector with a equalizer w and it becomes x. So this is not actually search, this is just sort of a a linear operator is here. So this linear operator will tell me we do not need to do the search. This linear operator will tell me what the exact value of x was. So that is the reason the option is option A. So let us go to the second question. The second question says, which of the following is not a design parameter? So design parameter says the parameters you can design inside the transmitter side or receiver side, and depending on them you can get an advantage over the signal processing sort of thing that is being done in the wireless communication. So digital decoder in transmitter side, it helps like just sort of mixing of the input signals to gain the advantage of the MIMO sort of thing. RF equalizer is also present in the as a equalizer format in the receiver side. RF decoder is also there in the transmitter side for the beam forming and beam pattern type of thing. So these three are necessary design parameters. So but wireless channel parameters between transmitter antenna and receiver antenna, so these channel parameters actually depends on the environment. Like if you change the environment, these design parameters will like you cannot design what is your channel. Like channel is a environment and it completely depends on the nature. So the wireless channel parameters between transmitter antenna and receiver antenna, option D, this is not a design parameter. So for question number 2, this is for question number 1, and question number 2 is option D. Now come to the question number 3. Question number 3 says the parameter in millimeter wave channel estimation are, so for millimeter wave channel estimation, but the first thing we need to do, we know that what is the angle of arrival of the signals and what is the departure of the angle of departure of the signals, and we also have to know what are the channel coefficients. Like for a particular beam it is going through a direction and we have to know what is the coefficient for that type of thing. So that is the reason for question number 3 we have to estimate all three, like angle of arrival, angle of departure and channel coefficients. So for question number 3 the right answer is option D. Question number 3 is option D. Now let us go to the question number 4. So question number 4 says, suppose we are sending the digital data stream of S and the element of S vector is coming from 5 different independent input data source, and the question is asked, what is the off diagonal entries of the covariance matrix RSS? So this question number 4. That is a vector S and this contains S1, S2, S3, S4 and S5. So what is the covariance matrix? It is expected value of S, S, T. So it is like expected value of S1 dot 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 S5 and S1 dot 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 S5 whole over expectation over all these matrices. So if I calculate this, it becomes expected value of S1 transpose dot 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 S5 S5 transpose. Okay, but if I say off diagonal element, the first off diagonal element will be S2 and S1. So if I think like that, this term, like for this case we don't need to write a transpose as we are already writing it like this. If we take the Hermitian operator here, then these things are coming like this, and this is S2 S1 star. This is actually S1 star and S5 star. Star. So the value of expected value of S2 and S1 star is equal to expected value of S2 and expected value of S1. So actually this term comes, what is the mean of this? Like if I take a QPSK constellation, the mean is 0. So anyway these two are independent and the mean is 0, so that makes the off diagonal entries as 0. So all the off diagonal entries will be 0. Only the diagonal entries will be there for the covariance matrix, and depends on the this depends on the power of the constellation. S1 S1 star, that is actually expected value of mod of S1 square. So this is actually quantifies the mean square, and mean is 0 for any constellation. So this actually implies the power of the signal. So the off diagonal entries are 0 and the diagonal entries are power. So the question is asked about what are the off diagonal entries of the covariance matrix RSS. So it will be 0. The option is option B. So let us go to the next question. The next question says, for a MIMO system, the data model is y is equal to hx plus w. So the data model is linear data model if the matrix H is not a van der Waals matrix. So let us think y is equal to hx plus w, and H is the channel matrix here, and y, x, w are respectively, like y is the received signal vector, x is the input signal vector, and w is the additive white Gaussian noise, and HP denotes the pseudo inverse of the channel matrix. The question in this is asked, the LMSE based equalizer depends on what? So RYY is the covariance matrix for the output signal, RXX is the covariance matrix for the input signal, and RY is the cross covariance sort of thing between X and Y. So it is asked how the LMMSE based equalizer depends. So if I talk about LMMSE based equalizer, what it actually does, this is for the question number 5. So the LMMSE based equalizer, it actually what it does, suppose we have a data model like this, so we don't know, like we define equalizer W such that W and Y, if I multiply W, it will convert to X. So if it is so, then probably it may not be X. Suppose WY equal to X dash, X hat, and there is a small error between X and X hat. So for which W, this X will be close to X hat. So what we do, we minimize X minus X hat, and this in terms becomes like you can say minimize Wi minus X. over the W. But this is not a search algorithm here, because this is just optimization problem, and this can be solved by taking the norm 2 of this. So what is the estimated W? What is this matrix W that transforms y to x? This transforms y to x. So what is that W? If I derive this equation, like, and the first thing is we have to define is wy minus x into wy minus x star, and then I have to minimize it over what? The W, because W is the parameter over which I am minimizing this whole thing here. So that is the reason. So if I derive this equation and equate it to 0, the whole thing, this is the cost function norm 2, so it becomes, W becomes RYY inverse into RXY. What does that mean? If I multiply WY, it becomes x. So RYY inverse into RXY into y, this is actually x, whole thing. So this is just a matrix multiplication with y, and it converts it to x. So let us check the options. So it depends on RYY and RXY. So we have to write RXY, the cross covariance term, and the variance term of the output signal RYY. It only depends on these two. So that is the reason the correct option is option C. So the next question is question number 6. Which of the following is true for MAC? The first option is we are minimizing the cost function based on 2 norm only.
Excuse me, sir.
Okay, tell me.
Sir, fifth one,
Your voice is not audible. Hello? Can you type in the chat box?
fifth question.
Fifth question is option C.
Okay, sir. Thank you.
So the sixth question is, which of the following is true for MAC? So the first option is we are minimizing the cost function based on 2 norm only. So second option is we are minimizing the cost function which is the expectation value of 2 norm cost function. The option number C is we are minimizing the expected value of 2 norm with the assumption that the estimated value will be linear function of the observed value. And the last option is none of the above. So let me tell about the thing. So you have a signal Y, and you know you have something like this. Your job is to find out the X. So for the first time, probably you just ignore that W. So probably you have Y is equal to Hx. So if I don't consider what is that noise W here, statistics, so what happens? Whatever we receive the signal, we try to find out what X is this. So we know what H by what channel estimation. So H is known to us and Y is also known to us, because Y is what we received in the receiver side. X we don't know, that is our job to find out. and probably W is some noise is there. So first task is we have to find what is the X. So if we don't consider about the statistics of the noise and all these things, what we can simply do, we can think Y is equal to Hx, and we can find out what is the X value. Like X will be H star H whole inverse H star Y. So this is what, this is actually the least square solution. And here we don't take what, the statistics of noise. So it is actually minimizing Y minus Hx square. The next thing is we want such estimation that makes Y minus Hx mod square and the expected value of this. This is what minimize the, what is this? This is mean, and what is the term here? Square. So this is the minimize the mean square. So that is MAC sort of mean square error. Right? So whatever, Y can be anything, but we just try to estimate it on some function of X. So what MAC actually says, take the expected value Y minus f of X and minimize this term. If I take Y is a linear function of X, it turns out to be LMMS. Like if f becomes Hx, what is our previous case? So the assumption is Y is a linear function of X, so that is linear, the term linear is added before MAC. But MAC can be anything, the function f defines it. So according to the questions, we are minimizing the cost function, which is the expectation value of true num cost function only. But the first thing is we are minimizing the cost function of true num only, that is not, because we are, the term expectation is here it is not, and it is also not a linear function, because if we take the linear function it will be LMMAC. So the correct option is here option B. So this has a code, option B. So let us go to the next question. So the next question is, what is the unit of channel capacity for unit bandwidth? So let us solve the question number 7. What is channel capacity? It is data rate per bandwidth. So unit of data rate is bits per second. This is hertz. So the unit is bits per second per hertz. So the correct option is option number 10. The seventh question answer is option number 3. Let us move to the 8th question. It says, for a MIMO system, the data model is y is equal to hx plus w, where h is the channel matrix of a dimension 5 cross 4, and as the question was same as the previous question was, so it is asked the least square based equalizer depends on what. So the least square based equalizer, as I discussed earlier, it does not take any statistics about the data, it does not take any statistics about the noise, it's just take the matrix H, calculates the pseudo inverse of the matrix, that is HP here, and after that it just multiply that with the pseudo inverse and it gets the output. It never takes the, so the probably the results will be bad, BR will be bad for least square sort of thing rather than the LMSE sort of thing, but that is simplest thing that anybody can do for equalizer design sort of thing. So the right option is option B for question number 8. Question number 8. So let us go to the 9th question. The question is asked, the covariance matrix RXY depends on what? So let us calculate this and we will find the answer here. It is asked to calculate the cross covariance term RXY for a linear data model. So if you think the model that is a linear model, so the term RXY it just gives what is the expected value of y x, or I can rather write it like this, as it is xy, it is x y star. So let us replace this x into hx plus w star of this. So this becomes expected value of x is to h, sorry, x star h star plus x w star. So this becomes r xx into h star, where r xx is the expected value of xx star, and this term becomes 0, like expected value of x w star, this term is 0 because noise is uncorrelated with input signal. So this only depends on RXX and H star. So RXX and H is the answer. The answer of the question number 9 is C. The last question. The last question is about the covariance matrix RYY depends on what. So let us calculate what is RYY. Similarly, like that. This is like Hx plus W star into Hx plus W. It is star here, after star there. So this is what it becomes. Hx x star plus W x star plus Hx W star plus W star. So this is what? This is expected value of W star is equal to RWW. And if I take the expectation over this, it becomes RXX. And it is also dependent on the channel type factor H. So the right option is option that contains all the factors RXX, RWW and H. So let us check. So option number A is contains all the answers. So the right option is option A. Okay. One more question I will try to address. So the question is, it says suppose X is a transmitted signal. And it has a power spectral density that is probably sigma square. And the sampling time is 1 millisecond. So what is the power? So the PST is sigma square, and as it is PST, the unit is watt per hertz. So the sampling time is 1 millisecond. So the sampling frequency is 10 cube hertz. So the question will remain here. So what is the total power here? So this will be 10 cube, and the power is sigma square, and it will be, the bandwidth will be 10 into 10 to the power cube. Why? Because this is a sampling frequency. So bandwidth of the signal will be this. So this will be like 2 into 10 cube sigma square watt. Okay. So any more question for today? So if not so, we can meet in the next class, I think.
Sir,
Yes.
it's audible.
Yes, it is audible.
Sir, possible to discuss assignment number 6, question number 10, sir. During that day discussion time, we were discussed only 9 questions. That 10th question is missed. Possible you can discuss the same, sir.
Which one? Previous day?
Yes, 6, question number 10.
Question number 10. What was
Previous week.
It's like I cannot remember the question, so let me check it once more.
Okay.
Yeah, question number 10, it was what, like QPSK constellation 5 input data stream, that question it is. Hello? Am I audible?
Yes, sir.
Which question it is, like 5 input data stream in the input of digital recorder, that question?
Sir, our question as well as your question is different, sir. That is the reason I am asking. For us, it is the question number 10 is correlation matrix. Suppose some values are given for Y matrix, have to find the correlation matrix of given. That is our question. Number 10 is available on the.
What was the question number of my question? Like,
I'm not sure, sir. Yeah. Is it possible to view the question number 10 in assignment 6?
Question number 6. Okay, let me wait. Your that question is
For us, question number 10 in assignment 6 is correlation matrix. Find the correlation matrix of given Y matrix. Is it same way? It is no problem. It is different way. Just we want to know what is that.
assignment number 6, right? Assignment number 6.
6, yes. Yes, 6. Assignment number 6. In chat box as clearly mentioned.
Okay, the options are probably not according to the van der Monde matrix here. Like what I had discussed, it will be like the first row will be like 1, it will be j theta 1. Like it is the question, the steering matrix formed at the receiver side of the 3x3 antenna system, right? This is the question, right?
Okay, sir.
What is the question? The steering matrix formed at the receiver side of the 3x3 antenna, that is the question.
Sir, our question bank is different from yours, sir.
Yeah,
That is the reason I am asking.
It is your question. It is your question. Tell me what is the question number of assignment number
In my question, in question number 10, in my assignment 6, question number 10 is based on the correlation matrix of the given matrix.
Okay.
Find the correlation matrix of given matrix. This is our question bank assignment number 6, question number 10.
Okay. That is your point.
So it is correct only. For me, I got the correct answer. But I want to know what is discussion on previous question paper.
Oh, the discussion. Let me check what is the discussion they have given. Okay. So the vector that is given like y is equal to 0.8 and 0.2 transpose. So let me solve that here.
This is same question is available for us. The answer is 0.64, 0.16, 0.16, 0.04.
Yes,
Transpose matrix, the correlation matrix.
like
The same question is the
what explanation you want from me? Like you, like
no, explanation is not good. The same question it is not, there is no need for explanation. I got the answer. I solved it. No problem.
okay, that is like uh, can you type in the chat box what is your problem, because your voice is breaking. That is the problem. I'm not actually clear what your problem is, so it is better if you type in the chat box. No, I know the problem. What is your query about that problem? That is I'm asking.
Last is not discussed. That's all.
Okay, it is not discussed.
Yes, that's the reason I want to know what is the question in that. That's enough. The same thing is repeated with no problem, sir. Thank you.
Okay.
Everything okay.
That's fine.
So what about final assessment questions, sir? It is related to our previous assignment related to questions will be there or any other things it will reflect.
The last exam,
Yes, sir. Final assessment.
that will be somehow different from all these things. Like I probably you.
On the whole assessment, first give the assignment.
Yeah, can you please type? Like your voice is too much breaking. Like I can't interpret any of it.
Okay, sir.
Sir,
Yeah.
excuse me, sir.
Yes.
Sir, where can we get the previous paper, sir?
Previous year access probably you will not get because you are enrolled. Previous year access probably you will not get because you are enrolled for that. That is only available to me. So I have no authority to give you the previous year questions. So,
Sir,
huh.
for practice we need some previous paper, sir. Likewise.
So okay, if I get the previous year question paper, I will send to you. Like next day, I will share the link. Is it okay?
Okay, sir.
Okay.
Okay, sir. Like, last year model paper, weekly assignments and final exam paper. If we have
See,
that, we'll have
last year
some
weekly
good practice for our
last
final
year
exam,
weekly
sir.
assignments are most of the things you are doing in this year. So assignment questions are mostly same. And the last question I will try to get it if it is possible for me, and if I get, I will discuss the last set question paper for the next class, next Tuesday. I will try to get it by at least 2 weeks. I will try to get it. Okay.
Okay, sir. Thank you. Thank you, sir.